Welcome to Physics Videos. Our topic today is free fall motion. Ever since we noticed that objects fall, we have been trying to explain how and why they do this. One interesting theory about falling objects was proposed by Aristotle. Aristotle's idea was based on his theory that everything is made of four elements. They are fire, air, water and earth. According to him, and I should mention that we no longer think this way, each element had a place where it naturally existed. The element earth would be found on the earth. Water naturally exists right next to the earth, air is found above water and fire naturally exists in the sky. Aristotle would explain that the process of burning a stick reduces it to its elements. We see the fire moving upward, into the sky, and the ashes would be the earth component. According to this theory, objects would move based on the ratio of each element that they contain. Things made mostly of fire and air would naturally rise, things made mostly of earth would naturally fall towards the earth. Further, Aristotle explained that the reason an acorn falls towards the earth at a greater rate than a leaf, is because the acorn contains more earth than the leaf. For a long time nobody worried too much about his explanation. We all know that if a leaf and an acorn fall at the same time, the acorn will land first. It wasn't until Galileo started thinking about Aristotle's elements that anyone really questioned his theory. Galileo liked to pose hypothetical problems and he came up with a good one for this situation, taking Aristotle's explanation about the acorn containing more earth than the leaf at face value. Galileo asked what would happen if an acorn attached to a leaf fell. On one hand, the acorn-leaf combination would contain more earth than an acorn by itself and should therefore fall faster. However, the acorn-leaf combination would also contain more air than an acorn by itself because of the added leaf. This suggests the combination should fall more slowly. Using Aristotle's rules, Galileo arrived at two answers that did not agree. This led him to think about other reasons the leaf might fall more slowly than an acorn. Galileo's answer was that it was the resistance provided by the air that made the leaf fall more slowly. He went on to suggest that if the air could be removed, all objects would fall at the same rate. An updated version of Galileo's theory is what we currently use to explain how objects fall. We use the term free fall to describe falling with no air resistance. Isaac Newton explained that if there is no air resistance, then the only force acting on the falling object is the attraction of the earth, what we call the weight of the object. In this situation, the acceleration of the falling object is 9.8 meters per second squared. Let's take a look at the equations of motion. Remember, these relationships come from our analysis of motion graphs with constant acceleration. Now, let's see what happens when we substitute a equals minus g. Negative 9.8 meters per second squared. The acceleration vector points in the direction of the gravitational force, towards the Earth. We have established a system that defines motion towards the Earth as negative motion, so any vector pointing towards the Earth would also be negative. The acceleration does not change as the object falls. However, if the falling object is moving downward and accelerating downward, it will gain speed. The equation shown allows us to calculate the velocity of the falling object. The velocity for objects falling towards Earth should also be negative, because down is the negative direction. Because it is gaining speed, a falling object will travel farther during each second of its fall than it did during the previous second. The displacement of the falling object is negative because, again, it is moving towards the Earth. The equation shown here is how we can determine the amount of displacement for the falling object. Now, let's take a look at a falling object. This picture shows a ball at rest, high above the ground. We will start our clock the instant we let go of the ball. It hasn't moved yet, so its original velocity is 0 and its displacement is also 0. The acceleration will be negative 9.8 meters per second squared for the entire time it is falling. This picture shows the ball 1 second later. Use your formulas to verify that it will have gained 9.8 meters per second of speed and it will have fallen 4.9 meters. Another second has elapsed. The ball is now traveling 19.6 meters per second towards the ground and is also 19.6 meters below its starting position. Verify these values. After 3 seconds of falling, it has reached a speed of 29.4 meters per second and is now 44.1 meters below its starting point. Notice that the spacing between images of the ball is increasing as it falls. This shows it is gaining speed. After 4 seconds, it is traveling 39.2 meters per second and has fallen 78.4 meters towards the ground. Here is what it would be after 5 seconds of falling. Check the values using the motion equations. After 6 seconds it is moving pretty fast and has traveled almost 2 football fields worth of distance towards the ground. I hope this video has shed some light on how we can determine the motion for an object in free fall. The key to all of these calculations is the fact that in free fall, the object has a constant acceleration of 9.8 meters per second squared acting downward. This is because there is no air to get in the way of falling. Now let's see how this really works if there is no air.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct in his findings.